Okay, guys. So I'm trying to probably won't do a full class today, but I'll just do enough so that we don't kind of get behind schedule because we've got quite a tightly packed schedule. So confidence intervals. So going back to the example I gave you in class, imagine we're trying to sample how many calories the average Mississippi State student consumes in a day, and we sample 50 students, and we get an estimate of 2,500 calories. Now, the population, all the students in the university, is not going to be exactly 2,500, but it's going to be somewhere close. So, what confidence intervals there is just give us this measure of confidence of the actual population mean. So, we get an interval of the population mean, and we'll say a certain percentage of time the population mean will be in this particular interval. So let's just have a few more little scenarios. So Mitsubishi got in trouble. They were forging their fuel economy results. So we get a sample of 50 vehicles, and we're going to basically try and make the experiment as fair as possible, as random as possible, and we record the miles per gallon for each of the vehicle, and then we use it to get the overall kind of population, in this case for the car in general, for the fuel economy. Going back to our competency test, we have a competency test, and we want to see if the average score, is greater is 70. So we fact test 50 employees, and we get a bounded range for how competent our employees are. And finally, let's have a proportion example. I really should have updated this slide. So you have worked with a software company, you have to estimate of the proportion of users still using, let's say, Windows 10. If this is less than 20% or 0.2, you will downgrade support. So we ask 100 customers which operating system they use, and then we get a range for the proportion. Okay, so let's go, and before we define things like coefficients, let's just do a bit conceptually on what I'd say is the board, but is in fact my little personal whiteboard here. So we defined before sampling distribution. So let's just imagine this. And this can be anything. So it could be, taking out 50 students for the calories, taking out 100 consumers and asking how much they spend on the outdoors. And each time, remember, with the sampling distribution, we get a sample mean. So we kind of get 50 consumers, we get a sample mean for our quantity, etc., etc. And if we keep doing that, then we get the sampling distribution. My beautiful normal curve here. And recall that, as we did last class, I'm not going to do the formal definition, for n is greater than 30 by the central limit theorem. This should be normal or Gaussian. And we had a few other properties, and so the expected value of all of these sampling means is going to be the overall population mean, is going to be in the center of the distribution. And our standard error of the sampling distribution, which is basically just the I'll put in brackets, standard deviation of the sampling distribution. That's going to be sigma, our population mean, over root n. So it's all the stuff we talked about last class that, as we get bigger and bigger samples, we can become more and more sure that we're close to the population value. So our standard error of the sampling distribution gets smaller and smaller. And quite often we don't actually know this information. So we just estimate it with S over root n. So what's the confidence interval? So I'm going to draw up here, and I'm going to call this 100%, 1 minus alpha, confidence interval, for the mean, which is mu. So let me draw a nice little line under that. Essentially, all we're doing is we're taking this sampling, and this is a very not a very technical class. I'm going to call this a flip. Okay, so let's just draw. What happened there? Go back to the ink pen. Let's draw here. And you see here, we have maybe one of these x's, and we can kind of make inference in this distribution here. So we've got, the majority of the x bars are in the center, and as you go to the edge, we have fewer and fewer and fewer. We want to almost flip this around. So we take an x bar, and we try to find inference of where the mean is. You see the mean is in the center here. So what we're doing here is we're just flipping it around and putting the x bar in the center, and then making inference on the mean. Now, if you notice here, we've got the level of confidence. Let's just say, and I'll define this a bit more formally in a second, but let's just say our alpha equals 0.05. This is our confidence coefficient. Then our confidence interval is 100 times 100% times 1 minus 0.05 is 95%. And what we do is, if this is our kind of, we flipped it around, so we have our our sample mean here, and we have kind of the distribution values where this mu can be, is we want to include 95% of them. So let's stick with proportions, 0.95 in here, which is going to be 1 minus alpha. And here, we've got alpha left, so this is going to be alpha over 2, which is going to be 0.025. And here, we've got alpha over 2, which is going to be 0.025. Now, remember, this is a normal distribution. We talked about how we can get the z-score. But, when we had a z, we had a mean of 0 and a standard deviation of 1. Here we've got a mean of x bar, so we can start off with x bar. That makes a lot of sense. But we kind of, we have this standard error. So our distribution is stretched out to sigma over n or s over root n. So we do this point here is going to be plus z sigma over root n. And in the opposite, subtract, it's going to be minus c sigma over root n. And then we can find, all this is this would, for example, be z 0.025. And we can look it up in our table in our book. So let's just do teaching, and let's do stats. And let's look at our statistical tables, the normal table. I had a better version of that. Let's look in my new statistical tables because they're nicer. And let's look at the beyond z. And we want 0.025. So we need to get a bit further down here. Oh, we've got there. And we see 0.025 is exactly 1.96. So our z value here, let me get the right one, is going to be 1.96. So let's just do equals 1.96. And we can kind of plug this in to get our kind of equation for the confidence interval. Okay, so let's kind of now do a slightly more formal definition. So let's just make this a little bit smaller. Let's move ourselves out of the way, and let's just write this definition. Oh, we don't want to see dolphins. Yeah. Just give me a second. Okay, so let's resume. And we have 100%, 1 minus alpha confidence interval for mu. And this is going to be kind of a large sample. So this is going to be this is going to be for the Z score. So basically the Z version of this. And I keep pressing random things. Now, I'd give you kind of a proper definition because we're using frequentist statistics. So I'd say in the long run, out of every 100 experiments, the true population mean will be in the confidence interval a 100 kind of 1 minus alpha times. So in this instance, it would be in 95 times. So the idea is we're in the long run, this 95 will hold. That's a little bit wordy. Not statistically too correct, but most people will say if I'm talking to a manager in a business, you'll just say I'm 95% confident in the result, for example. This would be the succinct way of doing it, not the statistically correct way. So if I gave the above to a manager, they would just think I'm being silly and overly wordy. And we can define it a little bit further. So let's just move down a little bit. So if we know, so if we actually know sigma, then this is going to be x bar plus or minus z alpha over 2 sigma over root n. And if we don't know sigma, we approximate. Now, the thing is, it's unlikely that this test, if we don't know the sample, if we don't know the population mean, we're unlikely to know this population standard deviation. So we just have to usually just estimate it from the sample. Most statisticians really, don't like this approximation, which is why they tend to use the sampling distribution, the t distribution. But that's kind of a topic for a different class. So generally, we're going to be, this is the formula that we're going to be using. And we have, I just showed you the example of the 95%, we use 1.96, but a 90%, we use 1.645, 99%, 2.575. Just kind of a few little hints. Let's go back to the board. So, and I'd usually do this as a shout out in the class, just to make sure that you're kind of awake. But let's just say if my alpha goes up, say it goes up from 0.05 to 0.1, that means that my percentage confidence interval, my percentage goes down. And that tends to be, that means my alpha, the bits at the edge of the distribution are getting bigger and bigger and bigger. So my confidence interval gets narrower. So my confidence interval gets narrower. If my S goes up, you can see that, and again, a standard deviation is our kind of level of uncertainty. So if our level of uncertainty goes up, then obviously we're going to be less confident. Our confidence interval is going to be narrower. So here our confidence interval goes up. And if my n goes up, remember I talked about eventually, we don't prove asymptotes in this class, but if my n gets to almost the size of the population, I pretty much have the population mean. So I don't need a confidence interval because I know the kind of what the actual population mean is. So my confidence interval goes down. And also you can see this is on the bottom of the confidence interval. A few other little things. We have the kind of the conditions of the test. So all these statistics, and quite often I will admit I can be guilty sometimes. Some of the examples in the textbook are not really random samples. But we have a random sample is selected from the target population. And 2 is the sample size is large. Sorry, I better put the n is the actual sample size. So sample size n with n greater or equal to 30. Okay, so let's do this on a specific data example. So we have, and sorry, apologies if this is a slightly sexist example, it's one from the book. So we have all women who shop on Black Friday. Now I hope they actually kind of basically they sample women about what their Black Friday shopping habits and ask how many hours do you go out shopping on Black Friday. For those international students who are in their first year here, Black Friday is this commercial event after Thanksgiving where there's lots of sales on, and you always see chaos of people fighting at Walmart for the best deals. So it's basically we should assume that people are contacted outside of the shopping environment in a random sample. If I went to the shops on Black Friday and grabbed people from there, then that would definitely not be a random sample and that would not be valid. So we have this in Excel. Now, for all of these examples, I kind of try and give you an Excel example. So here we have, actually in column A is the data set. So we have, our coefficient alpha. Here we define that. We have our data set. We actually calculate the mean, our summary statistics here. So we calculate the mean using the average function. Notice if I go to 10,000, that's just basically means it will work with any data set less than 10,000. So that's just a bit of a bodge to make sure that I could add extra numbers to the hours and this formula would still be valid. If I'd put A2 to A39 and then added an extra data point, then it wouldn't be. So the standard deviation. Now, Excel has sddev.s and p for sample and population. If you don't include either, the standard function actually gives the sample. And then we calculate the s over root n, so the standard error. We're actually going to do this one, the CI basic. And then you can see we're going to use, as we used for the previous week, we're going to use the norm.inverse function. So this is basically you pass in the alpha. Remember, the distribution in Excel goes left to right. So what the book calls minus alpha over 2 is basically alpha. In this case, it's going to be 0.025. So we get the z value for 0.025, which in fact is going to be negative, and it's on the left-hand side. And then we multiply it by C4, which is S over root n. So this is what we call our, basically, what we're subtracting, our margin of error. And then we do the same for positive, and this time we're doing alpha over 2, but as I said, Excel goes left to right. So in fact, this is 1 minus alpha over 2. And again, we multiply by the standard error and add to the mean. And this gives us our confidence interval for the mean. Now, Excel also has exactly the same, but it also has a confidence function. It has a shortcut. And here we put confidence.norm. We'd include the n, and we'd include the alpha and the standard deviation. And basically what this would do is this would give what we call the margin of error, the amount we subtract and add to X bar. So we subtract confidence.norm and we add confidence.norm. But to be honest, it's not actually much simpler than doing what we would do if we were calculating manually. Okay, so remember some of those values for the mean and standard deviation. And we're now going to kind of plug it in, and we're going to do the confidence interval. Okay, so let's move up a little bit. And we're going to get here. Okay, so let's just say we want 95% confidence interval. So, and again, you're going to probably know this off by heart, but 100%, we do 100% 1 minus alpha equals 95. So divide both sides by 100. 1 minus alpha equals 0.95. So alpha equals 0.05. Okay. And what we're going to do is, now there's different ways we can write this. We can do this, what I showed you before was the shortcut formula, x plus or minus z alpha over 2, sigma over, in this case, we don't know the population value, so we're just going to have to estimate. We can also write it a little bit, we can do the long form, because this is going to say we've got x bar in the middle minus plus. And what we're trying to do is we're trying to find an estimate for mu. So, but we could also write, and you can do the shortcut, but for the first time, I'm going to write it out. So we're going to have x bar minus z alpha over 2 s over n. We're trying to find the estimate for mu, so that goes in the middle. And then we have x bar plus z alpha over 2 s over root n. Now we can start plugging in the numbers. And remember, the s and the n are just what I got from the Excel spreadsheet previously. So you can look here, for example, and you see the mean is 6.0789, etc. So let's do that. So we could fill in 6.0789 minus, we already calculated the z alpha over 2 in the table before, so it's 1.96 times s, which is 2.7547. There was the sample size, the n was 38. And what we get is we get 6.07. So that should be that's a very badly drawn 8 on here. 89 minus 0.8759. So again, you just calculate this value. And again, the shortcut is fine that we actually calculate this value and then we add it and we subtract it. But even if you're going to do the shortcut, what I definitely want when you do the homeworks is I don't want you to end with like 6.0789 plus or minus 0.8759. I do always want you to give the final variant of the confidence interval, which in this case is going to be 5.205 to mu to 6.955. Okay, and that's our result. So we can say like 95 times out of 100, the true mean is going to be between 5.205 and 6.955 hours. Okay, so we've just done confidence intervals, and we're going to go further and do some additional confidence intervals as we go through the next few weeks, which is one way of getting an estimate of kind of variability of our population value from a sample. And now we're going to do another method, which is going to be hypothesis testing.